Are there any questions before I begin? So remember that there is a quiz tomorrow. I'll send you, as usual, the announcement after we're done with today's class on what's going to be on the quiz, and it will be about like finding like the derivatives of some functions, basically, which because that's what we have been doing. So yeah, so I'll send you that announcement after we're done today. Uh, the idea for like for today was just to continue talking about more rules for finding the derivative. So let me see, this would be lecture 9, I think. Let me double check. Yeah. So again, the goal is like to have like a bunch of rules for finding derivatives, and then using these rules, you can compute the derivative of more complicated functions. So we're almost at the point where we can start doing interesting thing in terms of computations. The next rule is like the derivative for the inverse of a function. Oh, sorry. Like that can be confusing if I write it like that. So let me write it like this: 1/g of x. Okay, so let me let me write what I mean by this. So if g of x, and you'll see why I'm calling this g of x. Before I have been calling them f of x, but it's more convenient in you'll see why in a moment to put it like this. So if g of x is a function that has derivative at x, and g of x is not 0, then g of x, oh, by the way, I should put this here. Well, no, let's just leave it like that. Then 1/g of x has a derivative equal to, okay, so there's like a formula for the derivative of 1/g of x, which is the following. Or alternatively, let me use a different color for this. I'll write it again, but with a different color. What color have I been using for this? Okay. So that's it. Like that's the formula for the derivative. If you write it in terms of the prime notation, otherwise, you can use it in terms of this Leibniz notation, in which case you would write it like this. And in this case, it's a little bit more, looks a little bit worse, but maybe. Yeah, and for this formula, like this looks a little bit like a little bit more confusing. But either like either is fine in terms of how you want to write this. Okay, is that making sense? I'm about again as always. I'll do some examples and like and the proof for this one I will leave for you to, so maybe I'll put here like the proof. I'll leave it for you to try it if you want to try it. It's not too bad of a proof. It may, I don't think if it's on the book directly, but you can definitely check it out. Like, so the proof, try it. But basically it involves, at least I'll write what it involves in terms of the limit. So, I mean, that would be the limit definition for the derivative of 1 over g prime of x. Okay. So that's the limit definition. And here you just have, like, if you wanted to compute it, like you just have to, put these two terms in a single fraction using the common denominator. And then you just play a little bit with, formula. It's not too bad of a proof, but, I don't want to like go over every single proof for like a derivative formula because then we would spend too much time. But it's kind of like, it's a good exercise if you want to practice like verifying these proofs because it doesn't have like a weird trick like the one from last time when we did the product rule. It's more or less straightforward. Um, oh yeah, let me do some examples. In fact, well, actually what's going to do is okay. Let's do let's do it with x squared plus 1. Like so. Yeah, let's do a couple. So let's say I wanted to so g of x. Let's say it's x squared plus 1. So what is 1 over g of x? It would be 1 over x squared plus 1, right? In fact, again, let me change the color here. So a problem could be like find the derivative of 1 over x squared plus 1, right? So the derivative of 1 over x squared plus 1, if you look at the formula, it is a fraction, right? Sorry, just to go up for a second. What you have to put here is a fraction. In fact, I will copy it again. It's a fraction where like in the numerator, you put like the derivative of g, and in the denominator, you put like the function squared. So let me put, and there's a minus sign that always comes from the formula. So it's minus g prime of x divided by g square of x. Okay. So what's the derivative of g of x in this case? It's 2x, that's good. Why is 2x? Because remember, like the derivative of a sum is the sum of the derivatives. So the derivative of x squared is 2x. And what was the derivative of 1? The derivative of 1 is zero because 1 is a constant, right? So I mentioned this probably like a couple of classes ago, but the derivative of constant function or a number is just 0. So this is, and then you just square the function. Is that making sense? Oh yeah, she's called Coco. Mhm. Um, and again, just in the other notation, this would be minus the derivative with respect to x of x squared plus 1 divided by x squared plus 1 squared. It would be minus 2x. I mean, it will obviously will give you the same answer. I'm just writing it in both ways so that you see like the differences in notation. Like the answer will be the same. So is that okay? Um, let's do another one, which is actually more important. So if you remember back, let's go back to trigonometry functions, back to trig functions. So in for trig functions, we have talked about sine and cosine mostly, right? So we had sine of x and cosine of x, or you could write them sine of theta, cosine of theta. For now, just to have like the same variable all the time, like we typically write them in terms of x instead of like writing sine of theta. But you could also write sine of theta, cosine of theta. That's okay. And so um, those are two important functions. The reciprocals, 1 over sine and 1 over cosine, they're also pretty important. So there is 1 over sine. I don't know if anyone remembers what is called 1 over sine. That's what's called the cosecant cosecant of x or cosecant of theta. It's called, or it's written as CSC, and that's 1 over sine of x, right? And you also have the secant of x, which is written sec of x, and that's 1 over cosine. Okay, so that finally these two make an appearance. I don't think we have used them before. But we can use this rule to find the derivatives of them. Okay, so for example, let's say I wanted to find I'll do the first one and I'll give you a chance to do the second so that you can try it out. So let's say I wanted to find the derivative of cosecant of x, right? What is the derivative of cosecant of x? That would be the derivative of 1 over sine of x, right? But now, if you see, like this is like the same rule as before, where this is g of x, right? This is g of x. So if you look at the formula for the derivative was put in the denominator, put in the numerator the derivative of the function and put in the denominator the function squared. So it would be, and there's a minus that comes from the formula. Is that making sense? Any questions up to this point? But then what was the derivative of sine of x? It was cosine, right? So you get minus cosine of x divided by sine square of x, right? And then that's the answer. That's actually the answer for the derivative. It's just that it is common to rewrite it in a different way. So you can rewrite this as minus cosine of x over sine of x times 1 over sine of x, right? At this point now, we are just playing with how it's being written. So we already have the answer. We're just like playing with it. Okay. So what is 1 over sine of x? I just wrote that for you, right? That's the cosecant of x. And anyone remember what is cosine divided by sine? There was also like a name for this one. I don't think I have given it, but it's what's called the cotangent of x, right? So cotangent of x. So what this is saying is that let me put it in a box because like it's very important. This is one of those you definitely need to memorize. So what we just found is that the derivative for cosecant of x is minus cotangent of x times cosecant of x. Or if you prefer the other notation, the derivative of cosecant of x is minus cotangent of x times cosecant of x. Is that okay? Any questions about this one? Okay, so let me give you like 2 or 3 minutes to try the following. Try doing the same, but for secant. So try to find the derivative of secant of x using the same idea. It's going to be exactly the same idea, but just like with a different formula. So try to do that and we'll discuss it like in 2 or 3 minutes to see what the answer is. Okay. Okay, so what should be the answer in this case? Yeah, it should be tangent times secant. Let's try to do it. Let me do it brief quickly. That's the derivative of 1 over cosine. If you look at the formula, put there's always a minus in the formula, and then you put the derivative of the function. So you have to put cosine of x prime here, and then you square the function, so cosine square of x. Okay? And then what's the derivative of cosine is minus sine. So you get minus sine of x divided by cosine square of x. And then the minuses cancel, right? So you get sine of x, and I'll break the denominator in a similar way. So this gives you sine over cosine is tangent, and then 1 over cosine is secant. Good. So again, this is one of those that you must memorize. That's why I'm putting it in a box. The derivative of the secant is tangent times secant. Is that okay? Any questions about this? So now, okay, so this is some illustrations of how to find the derivative for the reciprocal of a function. That's actually the word I should have said before, like 1 over that function. So the cool thing now is that you can, the next rule is kind of important as well. It's called the quotient rule. And as you might expect, it's a formula for the derivative of a quotient or a ratio, right? So here, f of x and g of x are two functions which have a derivative at x. And g of x is not 0, then f of x divided by g of x has a derivative. Okay, what's the derivative of the ratio or the quotient? Let me write it down and then we'll think about why they should be true. So the derivative of the ratio is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared. Or if you prefer to write it in the alternative notation, the derivative of a ratio of a quotient is the same. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared. And again, this is one of those that you must remember for sure. Um, so let me give you a second to write this down. Why, in this case, I'll do like the proof before giving some examples. So why do you think this one works? Like you could do the limit definition, but actually now we have enough tools that you can kind of prove this without using the limit definition. Is there a way that you can think for proving this without like going through the limit definition? Or let me ask it this way. Is there a way to think of a ratio as a product? what can I multiply? What is this equal to? If I wanted to think of this as a product, what should I put here? 1 over g of x. Good. Is that making sense with everyone? So what that means is that you can actually apply the product rule here. So you can apply the product rule. Because now we know, like, thanks to what we did before, we know the derivative of this, and we had seen the derivative of the product rule last time. Is that making sense? So let's think about it. What would be what does the product rule say for what is the derivative of this product? Let me put a big prime. So if you remember the product rule, it said the product rule was take the derivative of the first factor, right? Here again, I'm applying the product rule. The product rule says take the derivative of the first factor and multiply it by the second factor, and then do nothing to the first factor and multiply it by the derivative of the second factor. Is that okay? That's what the product rule said. And after that, we're almost done. So this thing, like, I mean, you can rewrite it as a ratio if you prefer. And then, oops, I forgot to put like the prime here. And then for this one, we have the formula for the derivative of 1 over g. So you can put f of x times minus g prime of x divided by g square of x. Okay. And so you see, like the only thing that happens between this and getting the quotient rule the way that I wrote it is that you just combine these two fractions or these two expressions. So to combine them, you can put g square of x as the common denominator. You get g square of x here. And that's where it comes from, basically. Is that making sense? Or are there any questions about this? Okay, let's do a couple of examples with the quotient rule. Again, I'll do the first one and maybe let you to work out the second one. So like the other two. So let me do one for you. So let's say I wanted to find the derivative of so let's say I wanted to find the derivative of this function. This is getting closer to the types of problems that I'll ask in general when I ask for you to find derivatives. it would be something more like along these lines where it's like a function that has been constructed out of functions whose derivatives you know individually. Okay. So if you look at this if you look at this expression, which is a ratio, the quotient rule says take the derivative of the numerator and multiply it by the denominator, and then subtract the numerator times the derivative of the denominator and divide by the denominator squared. Is that making sense? And then from after this, it's just more like finishing computing the derivatives. So the derivative of 2x plus 1, that's just 2 times x squared minus x. And then minus 2x plus 1 times the derivative of this thing. The derivative of x squared is 2x, and then minus 1. Okay, and that would be the answer. Like usually I wouldn't, yeah, that's what I was going to say. For these problems, I wouldn't ask you to simplify it first because like then it's easier for me just to grade it if you leave the answer like this. And yeah, if there's not much like, I mean, you just end up losing a little bit of time simplifying. So unless I want you to do something else with this derivative, if it's just like computing the derivative, you can leave it like that. You don't need to simplify it. If there were like additional purposes for the derivative, then yeah, you might need to simplify it, but not usually not for this type of problems. I would write explicitly simplify your answer or something like that if I needed you to simplify it. It's more like to check that you recognize that this is a quotient rule, that you know how to find the derivatives of the numerator and the denominator, and that you can put it all together, you know. Any other questions about this one? So again, let me give you like 2 or 4 minutes. Like think about the following two derivatives. So now with the tools you have, you can find the derivative for tangent and cotangent, right? But because what would be, here's another example. What would be the derivative of tangent of x? Well, the derivative of tangent of x would be the derivative of sine of x divided by cosine of x. And so you can apply the quotient rule to this one. And what would be the derivative of cotangent of x? Well, the derivative of cotangent of x would be cosine of x divided by sine of x. And again, you can apply the quotient rule to this one. So like, let me give you like maybe 3 minutes to think about this of what this answer should be, and I'll write it down after that because these are ones which again everyone should know what the answer is. Uh, okay, let me write down the derivative. Let me do the tangent derivative. The other one is exactly the same. So, and then I'll put the answers. So, for example, the derivative for tangent again is the derivative of sine of x divided by cosine of x, and so that is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared. So the derivative of sine is cosine, so you get cosine square of x, right? And then the derivative of cosine is minus sine, so you get minus sine of x times minus sine of x. So that's cosine square of x plus sine square of x divided by cosine square of x. Okay. And then hopefully you remember that there's this key identity that cosine square plus sine square equals 1. Right? And what is 1 over cosine squared? Well, 1 over cosine was secant, so this is just secant squared of x. Is that making sense? So that's how you find the derivative for tangent. So let me write them down because again, they're very important. So everyone should memorize these as well. So what we just found was that the derivative of the tangent is secant squared. If you prefer the derivative with respect to x of tangent of x is secant squared. And there's a similar one for cotangent, where the derivative of cotangent is minus cosecant squared. You mean oh, right. Oh, as an answer, yes, that would have been correct. It's just, I mean, that's correct. It's just that there's this identity that 1 plus tangent square is secant square. But yeah, like it just looks a little bit more like a longer answer. But yeah, you could have broken this as 1 plus tangent square. That's true. Yeah. It just looks you know, it looks like it has more terms. So it's just that's why it's preferred to write it as secant squared, but what you're saying is also fine. Yeah. So like just as an aside, yeah, this is the same as 1 plus tangent square of x. It's just that 1 plus tangent square of x is secant squared. So yeah, with this trigonometric stuff, there's always a bunch of different identities that you can use. So depending on which identities you end up using, the formula can look a little bit different. I mean, in in principle, this is also the correct answer, you know. It's just that that one does look a little bit more more harder to memorize, you know. So the derivative of cotangent is minus cosecant squared. And again, there are different ways in which you could write this because again, there are a bunch of trigonometric identities. And then the derivative of cotangent of x is also, if you prefer to write it in this other notation, that's how you write it. Is that okay? Are there any questions about it? Okay. So essentially, there's actually only one important rule left. We have more or less done all the major rules for derivatives, there's only one left, which is the most confusing, by the way, called the chain rule. So that's the one that actually does usually stand with respect to the others in terms of difficulty. Um, so the chain rule, that one, I don't want to address right now. I think it's more useful to start with a small detour on what the derivative does for you, because once we do that, it will be easier to understand what the chain rule is and why the chain rule works. So this is going to be a slightly different topic. So let's just take like a 5-minute break to switch gears, and we'll start like around 1:50, and I'll tell you a little bit more about what the derivatives does for you. And then if we have time, we do the chain rule, but if not, we'll just do it tomorrow. But yeah, let's take a 5-minute break and start with this new topic, if that sounds good. Okay, let's continue now with sorry, give me a second to change the microphone. I think that should be fine. Okay, yeah. So as I was saying, the chain rule is the only rule left of the main ones to find derivatives. It's just that the chain rule does require it's a little bit more tricky to understand why it works. So that's why I want to do a slight detour that should help us understand what's going on. So the detour just involves like two things. Another perspective of what the derivative is useful for. So the derivative, okay, so let me go this way, let me write it this way. So as a way to approximate a function. Okay, so let me write what I mean by this. So if you remember the graph of a function looks like a curve. And let me draw it a slightly different way. Okay. So this is the graph of a function. Maybe here's the value x, which has a corresponding value f of x, right? So if you remember, to find the derivative, which is the slope of the tangent line, right? What we did instead was like you can say, well, here you have x, you move to x plus delta x. Let me put it like here, let's say. In fact, let me move the function a little bit. Let me move the value x a little bit here. Okay, so you move to, like, you move by some amount delta x, right? And so if you move by some amount delta x, here you have x plus delta x, right? So this segment has like length delta x. That's a corresponding point above the graph, on the graph above this x plus delta x. That gives you like a value here, which is f of x plus delta x. Okay. And so there's a corresponding difference in the values for x, right? Which is what we were calling delta f. So delta f in this case is just f of x plus delta x minus f of x, because that's just the length of this interval that you see here. Is that making sense? So the derivative was like you would find the slope for the line going through these 2 points, right? And the derivative was the limit as x approaches 0 of that. So the derivative or the limit as delta x approaches 0 of delta f over delta x, or the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Again, there are many different ways to write the derivative in terms of a limit, but this is one of those ways. Is that making sense? So far so good. Okay. So what does this means? This means that once delta x is sufficiently small, right? This ratio should be a good approximation for the derivative, right? So like the idea of a limit is that you know, as you get closer and closer, in this case, as you get closer and closer to 0, this quantity will get closer and closer to what the limit is supposed to be. So the idea here is that once delta x is really small, delta f divided by delta x will approximate the value of the derivative. Okay. And so we write this in this way. Okay, so if you notice this, this is a symbol. It looks a little bit like the equality symbol, the equal sign, but it's not the equality symbol. It's just like a symbol that's used to sometimes to mean that it approximates it. So this is just like the approximate symbol, if you want to put it like put a name to it. So it's called like approximate symbol. Is that okay? Let me stop here. Just so far so good. Is this making sense? Okay, so let me give you an example of how this is used in practice. So imagine that I wanted to find, here's an example of how this is useful. So here's an example. What is square root of 4.1? And this will be like kind of like in the style of like problems that I'll be interested in you like answering. So this is kind of like the spirit of many of these calculus problems to approximate things. So what is the square root of 4.1? Okay, so here's one way you could approach this problem. We definitely do not know like an exact value for that. Okay, but there is a number close enough to 4.1 whose square root we do know. What is that number? We have this, we know the square root of some number that's close to 4.1, right? Well, we know even something that's closer to right. That one is even closer. It is true. The square root of 4 is 2, which is what maybe you were thinking about. So, but that's the whole idea. So good. So let's think about it like more visually. No, no, I got you. Like I thought what I think I knew what you meant to say. So, oops. So visually, right? This is the graph for the square root of x, right? You don't need to know like the graph too accurately, but I'm just drawing it here for our purposes. So what I'm saying is that we have x to be if we take x to be 4.4, right? We, if we take x to be 4, right? Then yeah, as you were saying, like the value for the square root of 4 is 2. So you have 2 here on the graph, right? And so what I'm going to do is move like an amount delta x, right? What's the amount delta x that I have to move? I have to move a delta x equal to 0.1, right? So if I let my delta x be 0.1, I'm going to be here at 4.1, right? And I don't know this value, right? But the moment I approximate delta f, once I know what an approximate value for delta f, I can kind of make a reasonable guess for what this should be. Is that making sense? Because then this is going to be the point what? This point is going to be 2 plus delta f. Oops. Is that kind of like, is the strategy kind of making sense? So what I'm trying to say is that what we're going to try to find is delta f, because once we find delta f, we add it to 2, and that would be like an approximate guess for what the square root of 4.1 should be. Any questions up to this point? So far, so good. So again, the idea is just to use this approximation perspective. So delta f, so again, like, let me put it like again, this is the main idea. Delta f divided by delta x should approximate the derivative, because we have decided that 0.1 is kind of small enough, or a small enough quantity. Of course, like then there's like a theory of how much of an error you're making by making this approximation, but I won't get into that. It's a little bit too detailed for our purposes. I'm getting more like trying to get like more of like a big picture of like what's going on. Okay. So what if you remember? Okay, hopefully. Okay, so this is what we're about to do. So f of x in this case is root of x, which is x to the 1/2. And so I gave you like, well, we did it explicitly for the square root of x. Anyone remember the formula for the derivative of the square root of x? You can use the power rule. The power rule said you bring down the exponent into the front, okay? And then what happened with the exponent after you bring it down? Anyone remember? There's something that had to be done here. You drop you lower the, right, you decrease the exponent by 1, so you have to put 1/2 minus 1, good? So this is 1/2 times x to the negative 1/2, and this was the same as 1/2 root of x. Is that making sense? So again, if you go to the approximate formula, this means that delta f divided by delta x should approximate 1/2 root of x, okay? But we want this, right? This is the approximation, but we want this for delta x equals 0.1 and x equals 4. Is that making sense? And so want to use this for delta x equals 0.1 and x equals 4. Is that okay? And so if you apply it for those values, you would get delta f divided by 0.1 is approximated by 1/2 root of 4. Right? So what is that? So that means that I mean, there are different ways to do this. So that means that what is delta f over 0.1? That's 10 delta f, right? I mean, there are different ways to write this, but let me do it this way. It's approximated by 1/2 root of 4. That's 1/4, right? Which is 0.25. So that means that the 10 delta f is approximately equal to 0.25. So delta f is approximated by 0.025. Okay, so let me stop here. Any questions up to this point? Is that making sense? So far so good? Uh, oh, okay. Let's see. Let me see where we have where the issue could be. So far I have it. Okay, so is this okay so far? So I'm just changing this to this, right? Is this one clear? Oops. Oh, sorry, I did something silly. Okay, and now the thing is, okay, and here I'm not doing anything yet. I'm just like rewriting this as a decimal, right? So I get to this point. Is this now where you have your question? Like, how do I get from here to here, or is it before?
So I had my question like on that first step where you converted from the delta f over 0.1. So I just didn't get, I get it now, but I just didn't understand initially why like you didn't. I guess I kind of thought you're multiplying on both sides to cancel the 0.1, but it
yeah,
makes
you could.
sense. But yeah,
You're right. You could also do
okay,
it that way if you prefer. Like, let me put it as an alternative way, right? So
okay, thanks.
if you have it, yeah, I mean that's like another option if you prefer. So once you have it like this, right? So you can multiply both sides by 0.1, correct? So you approximate it by 0.1 over 4, right? And then this is being approximated by 0.1 of times 0.1 times 0.25, right? Which is how we get the same. So yeah, you could it's up to you, like maybe this is more clear. Yeah, there are different ways to approach it, but yeah. You could also have like multiply both sides by 0.1. Is it better now?
Yes, thank you. Appreciate it.
Yeah, no, sure. So you see that this is delta f, and so what does this mean? Oops, I keep like choosing the wrong function on the iPad. So this means like the amount that f changed when you move by delta x, right? So if you go back to the graph, this delta f corresponds to 0.025. So that means that our estimate for like the square root of 4.1 is just 2 plus that like increase. So our estimate, so what we're saying is that 4.1, so our estimate is that the square root of 4.1 is approximated by the square root of 4 plus delta f, which is 2 plus 0.025. So so again, like what if you had to make an estimate, you would say that this is 2.025. Is that making sense with everyone? So that's how you would estimate what the square root is in this case. So in fact, if you go to Wolfram Alpha, for example, or if you have a calculator around you, let's go to Wolfram Alpha. You can put in Wolfram Alpha a square root of 4.1. And it gives you this, right? Which if you were to round it, you would get like 2.025. So what happens is that Wolfram Alpha or like a calculator or this more complicated computer, like algebraic systems, like what they do is like actually do like a better approximation of what we're currently doing. Okay, so there are ways to improve the approximation, but this is like it is a relatively good approximation for certain purposes. Okay, but like the important thing here is like kind of like it is like a useful tool to get like to understand like the values sometimes there are values that you care about, like again like square root of 4.1, where you cannot expect like an exact answer, but with this idea you can kind of get like something pretty damn close. Okay, so that's like one way to think about the derivatives. The derivative is giving you like a way to approximate values. Is that making sense? Let me see if I'm not sharing. Go back to the iPad. So I'll write it down again. Let me put the, oops. Right, so what's yes, just to answer this question in the private chat. So philosophically, what's happening is that like if you had chosen instead of 4.1, let me first go to the, let me make the iPad work first, and then I'll answer your question. Right, so right, for this approximation, we took a delta x of 4.1, right? But if we had taken like, you know, something like 4.01, right? Then the delta x here would have been 0.01, and that's smaller, right? So here you would expect a better, a value that's closer to the truth. Okay, so delta x, the moment you keep making it smaller and smaller, the approximation gets better and better. So this is smaller than 0.1. So this will yield a better approximation. Is that okay? So again, yeah, the philosophy is like the smaller delta x is, the better this will behave, because the smaller delta x is the closer like this auxiliary line would be to the tangent line. So the closer the two slopes would be. So that's what's going on. Of course, like again, like if you wanted to apply this to experiments or like data collection, you want to know sometimes like what sort of error are you making, right? Because an approximation is not that useful if you don't know the error. But like there are ways to like also say what sort of error you're making. Okay. So yeah, like I kind of giving you half the story. The other half of the story is like once you make this approximation, how bad is the error? And that can also be said. And I guess like if you take calculus 2, you may do some of it. But it's not something I'll get, at least we won't get into that. But yeah, there's like a theory of error, like of how bad, what happened when you did the approximation, by how much of the true value are you how far away could you be from the truth value, from the correct value. But at a minimum, philosophically, yes, the smaller delta x is, the better this is as an approximation. Okay, so so just to rewrite this, I mean, just to repeat the point. So the approximation is I mean, it is kind of nicer to multiply both sides of this approximation by delta x so that you don't see the ratio. So the way typically how you will see this is that delta f is approximated by f prime of x times delta x. It just looks nicer to have everything without fractions. So where delta f is f of x plus delta x minus f of x. So if you want, you could rewrite this the other way to write. I mean, this is one way to write the approximation, which is good. The other way to write it, if you don't want to write things explicitly in terms of delta f, is just to substitute delta f with this thing, right? And once you do that, what this is saying is like the other way to rewrite it is that f of x plus delta x is approximated by f of x plus f prime of x times delta x. Okay, so these two ways of writing it, they are equivalent. Okay, they mean the same formula, but they're but they're just being written in slightly different ways. Okay. This one is a little bit more explicit, but this one is, since it's less explicit, it's kind of like more of a summarized version of what's happening. So this one is nice because of that as well. Okay, so far so good. So now I promise like probably tomorrow this will like this detour will make a lot more sense of why I did it this way before giving you the chain rule. But so there's another way to think of this approximation, which is related to a different way to visualize functions. So typically, there are many ways to visualize functions. Like, so like let's just spend some time doing that. Okay, this is also useful. So what do I mean by this? So like what are some ways to visualize what functions? Let me do it with the one that I'm going to do it first. Okay. So one way is to do it like in the traditional way of the graph, right? So the first option is using the graph. So for example, if f of x is like 2x plus 3, right? Well, you know that this is the equation of a line, right? So the graph is a positive slope, so it's increasing line. It goes through 3 at the origin. Sorry, it intercepts the y-axis at 3. So it looks something like this, right? This would be the graph of f of x equals 2x plus 3, right? That's one option to visualize a function. There's another option which is like less used, but it's still kind of convenient, like more like from like if you were to put this like into like an Excel spreadsheet or something like that, more like from a data perspective. It's more like, let's call it a version in terms of like, I mean, in terms of what's called like a stat, but I don't know if you have heard this before. So let's call it arrows. So what do I mean by this? So what you could put, like another way to do this, like to represent this, is that you could draw kind of two X or two ovals, two circles. And so on the first circle, you're going to put the values of X, and on the second circle, you're going to put the values of f of X. So for example, if the value for X that you choose is 0, right? What's the corresponding value for f of X? That would be f of 0, but f of 0 in this case is 3, right? So what this is saying is that the value X equals 0 gets transformed to the value 3, right? Or gets sent to the value 3, which is what you see here, you know, in a slightly different way. Or if you take the value X to be 1, then and let's put like an arrow to indicate that it goes from X to f of X. If you take the value 1 of X to be 1, what value is this being sent? This is being sent to 2 plus 3, right? Which is 5. And just to give you one more, like say if you had put like the value of X to be -2, then what would this be sent to? It would be -4 plus 3, that's -1, right? Is that making sense? So visually, I mean, it's kind of maybe like an inferior way to represent like the function, but like another visual way to think of a function is like you have like on one bag like the values for x, and on a second bag you have like the values the function takes, and like the function what it's doing is kind of matching the values, right? Drawing some arrows between them. Is that making sense so far, so good? And like the third option, which is the one that I want to use right now, because that's the one that will be useful next time, is like kind of like an intermediate of these two. It's like a hybrid between option one and option two. And so what do I mean by this? I just mean that you kind of like the problem if you put it this way is that like the values are kind of like all over the place. They're not like arranged like the way you arrange them here where oops, I don't know why this died. Sorry. You see like here like the nice thing about doing it this way is that the values of x are in increasing order, right? But here there's kind of like not like such a nice way to arrange put them in an increasing order because they're being just being drawn on a circle. So what you can do is option three like wasn't state. So let me put it like again. So this one is a hybrid. Oops. So like the kind of like the conciliatory move is to use both ideas at once. So instead of representing this as a circle or some bag, I'll just draw them again for like a line. So I'll draw X here as a line. But okay, this is like collapsing for some reason. Let me, if not, I'll just open a new PDF because I think it's not being saved for some, maybe it like the file is too big, but that would be weird. So if this stuff fails again, I'll just like open a new PDF on the tablet. So what we're going to do is we're going to put the x values on the line, and also we're going to put the y values on the line. But it's like usually the y values are drawn perpendicularly to the x values, right? That's kind of like the approach here. But I mean, actually, there's no reason that says like that has to be done all the time. So it's kind of like a thing that you were told, but and maybe you never were told to question it. But like another option would have been to draw both lines horizontally, and that's what I'm going to do now. So for example, if I do that, I had the value for x to be 0, and that's being sent to 3, right? Okay, yeah, let me see if I think maybe the file is too big, so let me open a new file. Give me a second. And if this is failing, then I'll check what else could be the issue. Mm, okay, so I'll put this. So 0 was, again, f of x was what? 2x plus 3. So 0 was being sent to 3, right? Then I think, okay, I don't remember the colors, but we can put them here. Like we could have 1. Okay, now the iPad is kind of dying for some reason. I don't understand it. Let me see if I can fix this. Well, in fact, actually I had done it. Let's see. Give me a second. Where should I have? Let me bring. I'll try to connect the iPad to the computer. Maybe this instead of like doing the AirPlay. But let's just pause for like a minute or two while I fix it. So yeah, what I'm going to do is I'm turning off the tablet to see if that makes a difference. Even though I'll connect it to the computer, because maybe like doing it on the AirPlay mode for some reason could be um, more taxing on the tablet. I don't know, but at least it wasn't the size of the file. I don't think so. Let's see. We could connect it. Well, I might as well connect it to see if this is the. Okay, let's cross the fingers and hopefully this will work. Yes, I already did this. Okay, we'll see. We shall see. Sorry about that. So it was, can everyone hear me well, by the way? Okay, so yeah, 0, 1 to 3, 1, 1 to 5. Then I didn't do -1, but we could do it, right? So -1, where should I send -1? It should be going where? The function was 2x plus 3, so it would go to 1, right? Is it making sense so far so good? And you could keep going, right? So like for example, -2. Okay, at least it hasn't collapsed, so this is good. So -2 went to -1, and let's do that one more, which is 2 went to what? 7, right? Again, and the rule for this function was 2x plus 3. Is that making sense? Is this diagram kind of like reasonable and making sense? And now what? Okay, here's a cool thing. This is why this is kind of actually useful sometimes to draw it this way, because what's the spacing? What's the spacing between the points that I chose? By how much? By what amount are they all being spaced here? Or like what's right? Like that's the distance between these points. But what's the distance? What's the spacing between the corresponding points upstairs? It's 2. So the function, what it's actually doing, right? The function, what it's actually doing is if you take a delta x here, right? What color should I use for this? Let's use green. I don't know. Let's use gray, right? So I'm taking like, if you take a delta x, right, of 1, which I just chose for our purposes, the spacing here, the delta f, right, the delta f is the spacing between the output values is actually twice delta x, right? And that makes sense, right? Because if you remember, f prime of x for this function, right? What is f prime of x for this function? Is just 2, right? So the derivative, right? It is 2. So the derivative is actually telling you by how much this spacing is getting rescaled. So what happens in general, like like if you think about it as an approximation, is that when you have like some values, delta, so in the general case, you have some values delta x, which get mapped or get sent to some numbers here. Let me just exaggerate this. So like here's like a random, a general, and some function f of x. These get mapped to some numbers there, and then there's a corresponding delta f here. And the linear approximation, one way to think about it is it actually telling you by how much the values upstairs differ. So it gives you like a more like a like an interpretation of the function of the derivative as giving you like a rescaling between the distances between the values of x and the y values. Is that making sense? So just to show you a couple of like this is kind of what I was showing you here before on the PDF. You have like for this function, you have like some values for delta x, and basically the values for the output are twice as big. And they're twice as big because the derivative is 2. But then you could have something more complicated where you could have something more complicated like x squared, right? Where the derivative of x squared, if you remember, is 2x. So the amount of rescaling depends on the value of x that you choose. So there are some values of x where like the scale gets expanded, but there are other values of x where it gets shrunk. Okay, and that the expansion or a shrunken rate is given by the derivative. Is that making sense? So it's a cool way to think about the derivative. The derivative from this perspective is a way to know that shrinks or expands like the values for the function. And that will be useful tomorrow because tomorrow we'll talk about the chain rule, and the chain rule is called like involves like a composition of functions. So it just involves applying the function to functions. And from this perspective, you'll see the chain rule is more or less obvious. So, but again, I'll kind of we'll restart with that next tomorrow because it will be useful to just remind you about this. But it's kind of like a good idea to keep in mind. Just keep it on the back of your head for tomorrow's class. But I'll refresh your memories on Thursday. So yeah, I'll send you an announcement about the quiz in a couple of minutes. And well, it seems like, yeah, it's the iPad stopped collapsing, so this is good. But yeah, I'll send you the announcement in a couple of minutes, and if someone needs me, I'll go to the office hours. If not, I'll see you tomorrow. Bye.